Hi everyone, my name is Cooper Nicholson and this is my presentation for Physics 2212 Lab 4 Magnetic Field of a Bar Magnet. The purpose of this lab was to measure how the magnetic field strength changes with distance from a small bar magnet, determine its magnetic dipole moment, and compare our experimental results with a computational model that predicts the same behavior. In this experiment, I worked to measure the distance-dependent magnetic field of a bar magnet using a phone magnetometer app. From my results, I found that the magnetic dipole moment of the bar magnet was 1.38 and the slope of the distance-dependent relationship was negative 1.1534, showing that the magnetic field decreases roughly as the cube of distance. The main physics principles I applied in this lab include the Biot-Savart law, which relates the magnetic field at a point in space to a current element producing it, the magnetic field of a dipole, which models a bar magnet as a small loop of current producing a magnetic moment, and the general distance-dependent relationship where the magnetic field magnitude falls off proportionally to 1 over r cubed. Together, these laws describe how a magnetic field strength and direction vary as we move closer or further from a magnet. The system in this experiment was the magnetometer, while the surroundings included the bar magnet and the Earth's magnetic field. I began by setting up the phone with the magnetometer app, aligning it along the Earth's magnetic north using a meter stick. Then I located the magnetometer sensor chip in the phone using small pieces of tape and shifting it along the x and y axes until I identified where the readings changed most significantly. Once I had set the setup aligned, I recorded the on-axis magnetic field at various distances from the magnet, then linearized the data using natural logarithms. The slope of negative 3.1534 confirmed the inverse cube relationship expected for the dipole fields. When the magnetometer was far away from the magnet, it detected a very small or nearly zero field in the x direction. As I moved closer, the x component of the magnetic field increased, showing stronger interaction with the dipole field of the magnet. The phone's position also mattered. Aligning it correctly minimized interference from the Earth's magnetic field, ensuring that the field measured was mainly due to the bar magnet itself. From my linearized data, I obtained the equation y is equal to negative 3.1534x minus 15.102. I then found that the natural log of k is equal to negative 15.102 and that k is equal to 2.76 times 10 to the negative 7th. The magnetic moment was calculated to be 1.38. My magnetic field was in the x component 2.13 times 10 to the negative 5th, and in the y component 6.05 times 10 to the negative 5. The magnetic field predicted was in the x component 4.684 times 10 to the negative 6, and in the y component 1.504 times 10 to the negative 5. For the computational portion, I wrote a Python program that simulated the magnetic field vectors from a dipole placed at the origin. In the visualization, orange arrows represent the magnetic field along the magnet's axis, and blue arrows represent the perpendicular field. And a purple arrow shows the field at a 45-degree angle. This model helped verify that the field weakens and changes direction consistently with dipole theory. Here is the resulting code that went along with the computational model, showing both how the blue and orange arrows were calculated and the functions used to make them. Some discrepancies existed between my experimental model and my experiment and model results. The experimental model produced a field of 4.684 times 10 to the negative 6 in the x and 1.405 times 10 to the negative 5 in the y, while the experiment produced 2.13 times 10 to the negative 5 and 6.05 times 10 to the negative 5 in the y. These differences likely come from measurement and alignment errors. Possible sources of error include misalignment when finding magnetic north, nearby electronic or metallic objects that distorted the readings, or small tilts or shifts in the phone's position as it was moved along the meter stick. If I had not compensated for magnetic north, the Earth's magnetic field would have significantly interfered with the readings, leading to completely inaccurate dipole measurements. What if you were to stick two identical magnets together end to end and do the experiment again? How would the measurements differ? The magnitude of the results would be larger, not necessarily 2 times, but still larger with the same direction. To conclude, this experiment successfully demonstrated the distance dependence of a magnetic dipole's field and allowed me to determine a magnetic moment of 1.38. The results aligned well with theoretical and computational predictions, validating that the magnetic field of a bar magnet indeed follows the 1 over r to the third relationship. Thank you for watching.